Open Computing Language is a framework for writing programs that execute across heterogeneous platforms consisting of central processing units, graphics processing units, digital signal processors, field-programmable gate arrays and other processors. OpenCL includes a language for programming these devices, and application programming interfaces to control the platform and execute programs on the compute devices. OpenCL provides parallel computing using task-based and data-based parallelism. OpenCL is an open standard maintained by the non-profit technology consortium Khronos Group. It has been adopted by Apple, Intel, Qualcomm, Advanced Micro Devices, Nvidia, Altera, Samsung, Vivante, Imagination Technologies and ARM Holdings. For example, OpenCL can be used to give an application access to a graphics processing unit for non-graphical computing. Academic researchers have investigated automatically compiling OpenCL programs into application-specific processors running on FPGAs, and commercial FPGA vendors are developing tools to translate OpenCL to run on their FPGA devices. OpenCL can also be used as an intermediate language for directives-based programming such as OpenACC. Overview: OpenCL views a computing system as consisting of a number of compute devices, which might be central processing units or accelerators such as graphics processing units, attached to a host processor. It defines a C-like language for writing programs, called kernels, that execute on the compute devices. A single compute device typically consists of many individual processing elements, and a single kernel execution can run on all or many of the PEs in parallel. In addition, OpenCL defines an application programming interface that allows programs running on the host to launch kernels on the compute devices and manage device memory, which is separate from host memory. Programs in the OpenCL language are intended to be compiled at runtime, so that OpenCL using applications are portable between implementations for various host devices. The OpenCL standard defines host APIs for C and C++. Third-party APIs exist for other programming languages such as Python, Julia, or Java. An implementation of the OpenCL standard consists of a library that implements the API for C and C++, and an OpenCL C compiler for the compute device. Targeted memory hierarchy. OpenCL defines a 4-level memory hierarchy for the compute device: global memory, shared by all compute devices, but has high access latency. Read-only memory, smaller, low latency, writable by the host CPU but not the compute devices. Local memory, shared by multiple processing elements within one device. Per-element private memory. Not every device needs to implement each level of this hierarchy in hardware. Consistency between the various levels in the hierarchy is relaxed, and only enforced by explicit synchronization constructs, notably barriers. Devices may or may not share memory with the host CPU. The host API provides handles on device memory buffers and functions to transfer data back and forth between host and devices. History: OpenCL was initially developed by Apple Incorporated, which holds trademark rights, and refined into an initial proposal in collaboration with technical teams at AMD, IBM, Qualcomm, Intel, and Nvidia. Apple submitted this initial proposal to the Khronos Group. On June 16, 2008, the Khronos Compute Working Group was formed with representatives from CPU, GPU, embedded processor, and software companies. This group worked for 5 months to finish the technical details of the specification for OpenCL 1.0 by November 18, 2008. This technical specification was reviewed by the Khronos members and approved for public release on December 8, 2008. OpenCL 1.0, OpenCL 1.0 released with Mac OS X Snow Leopard. According to an Apple press release, Snow Leopard further extends support for modern hardware with Open Computing Language, which lets any application tap into the vast gigalops of GPU computing power previously available only to graphics applications. OpenCL is based on the C programming language and has been proposed as an open standard. AMD decided to support OpenCL instead of the now deprecated Close-to-Metal in its Stream framework. RapidMind announced their adoption of OpenCL underneath their development platform to support GPUs from multiple vendors with one interface. On December 9, 2008, Nvidia announced its intention to add full support for the OpenCL 1.0 specification to its GPU computing toolkit. On October 30, 2009, IBM released its first OpenCL implementation as a part of the XL compilers. OpenCL 1.1 OpenCL 1.1 was ratified by the Khronos Group on June 14, 2010 and adds significant functionality for enhanced parallel programming flexibility, functionality, and performance, including new data types including 3-component vectors and additional image formats. Handling commands from multiple host threads and processing buffers across multiple devices. Operations on regions of a buffer including read, write and copy of 1D, 2D, or 3D rectangular regions. Enhanced use of events to drive and control command execution. Additional OpenCL built-in C functions such as integer clamp, shuffle, and asynchronous threaded copies. Improved OpenGL interoperability through efficient sharing of images and buffers by linking OpenCL and OpenGL events. OpenCL 1.2 On November 15, 2011, the Khronos Group announced the OpenCL 1.2 specification, which added significant functionality over the previous versions in terms of performance and features for parallel programming. Most notable features include device partitioning, the ability to partition a device into sub-devices so that work assignments can be allocated to individual compute units. This is useful for reserving areas of the device to reduce latency for time-critical tasks. Separate compilation and linking of objects, the functionality to compile OpenCL into external libraries for inclusion into other programs. Enhanced image support, 1.2 adds support for 1D images and 1D/2D image arrays. Furthermore, the OpenGL sharing extensions now allow for OpenGL 1D textures and 1D/2D texture arrays to be used to create OpenCL images. Built-in kernels, custom devices that contain specific unique functionality are now integrated more closely into the OpenCL framework. Kernels can be called to use specialized or non-programmable aspects of underlying hardware. Examples include video encoding, decoding and digital signal processors. DirectX functionality, DX9 media surface sharing allows for efficient sharing between OpenCL and DX9 or DXVA media surfaces. Equally, for DX11, seamless sharing between OpenCL and DX11 surfaces is enabled. OpenCL 2.0, on November 18, 2013. The Khronos Group announced the ratification and public release of the finalized OpenCL 2.0 specification. Updates and additions to OpenCL 2.0 include shared virtual memory, nested parallelism, generic address space, images, C11 atomics, pipes, Android installable client driver extension, implementation. OpenCL consists of a set of headers and a shared object that is loaded at runtime. An installable client driver loader must be installed on the platform for every class of vendor for which the runtime would need to support. That is, for example, in order to support NVIDIA devices on a Linux platform, the NVIDIA ICD would need to be installed such that the OpenCL runtime would be able to locate the ICD for the vendor and redirect the calls appropriately. The standard OpenCL header is used by the consumer application. Calls to each function are then proxied by the OpenCL runtime to the appropriated driver using the ICD. Each vendor must implement each OpenCL call on their driver. A number of open-source implementations of the OpenCL ICD exist, including FRAOCL and OCL ICD. An implementation of OpenCL for a number of platforms is maintained as part of the Gallium Compute project, which builds on the work of the Mesa project to support multiple platforms. An implementation by Intel for its Ivy Bridge hardware was released in 2013. This software, called BeagNet, is not based on Mesa Gallium, which has attracted criticism from developers at AMD and Red Hat, as well as Michael Larabelle of Phoronix. Timeline of vendor implementations: December 10, 2008, AMD and Nvidia held the first public OpenCL demonstration, a 75-minute presentation at SIGGRAPH Asia 2008. AMD showed a CPU-accelerated OpenCL demo explaining the scalability of OpenCL on one or more cores, while Nvidia showed a GPU-accelerated demo. March 16, 2009, at the 4th Multi-Core Expo, Imagination Technologies announced the PowerVR SGX 543MP, the first GPU of this company to feature OpenCL support. March 26, 2009, at GDC 2009, AMD and Havoc demonstrated the first working implementation for OpenCL accelerating Havoc cloth on AMD Radeon HD 4000 series GPU. April 20, 2009, Nvidia announced the release of its OpenCL driver and SDK to developers participating in its OpenCL Early Access program. August 5, 2009, AMD unveiled the first development tools for its OpenCL platform as part of its ATI Stream SDK v2.0 beta program. August 28, 2009, Apple released Mac OS X Snow Leopard, which contains a full implementation of OpenCL. OpenCL in Snow Leopard is supported on the Nvidia GeForce 320M, GeForce GT 330M, GeForce 9400M, GeForce 9600M GT, GeForce 8600M GT, GeForce GT 120, GeForce GT 130, GeForce GTX 285, GeForce 8800 GT, GeForce 8800 GS, Quadro FX 4800, Quadro FX 5600, ATI Radeon HD 4670, ATI Radeon HD 4850, Radeon HD 4870, ATI Radeon HD 5670, ATI Radeon HD 5750. ATI Radeon HD 5770 and ATI Radeon HD September 28, 5870, 2009, Nvidia released its own OpenCL drivers and SDK implementation. October 13, 2009, AMD released the fourth beta of the ATI Stream SDK 2.0, which provides a complete OpenCL implementation on both A700 per Rankine 800 GPUs and SSE3 capable CPUs. The SDK is available for both Linux and Windows. November 26, 2009, Nvidia released drivers for OpenCL 1.0. The Apple, Nvidia, RapidMind and Gallium 3D implementations of OpenCL are all based on the LLVM compiler technology and use the Clang compiler as its front end. October 27, 2009, S3 released their first product supporting native OpenCL 1.0, the Chrome 5400E embedded graphics processor. December 10, 2009, VIA released their first product supporting OpenCL 1.0, Chromotion 2.0 video processor included in VN1000 chipset. December 21, 2009, AMD released the production version of the ATI Stream SDK 2.0, which provides OpenCL 1.0 support for R800 GPUs and beta support for R700 GPUs. June 1, 2010, SNI Labs released details of their first OpenCL implementation for the ZMS processor for handheld, embedded and digital home products. June 30, 2010, IBM released a fully conformant version of OpenCL 1.0. September 13, 2010, Intel released details of their first OpenCL implementation for the Sandy Bridge chip architecture. Sandy Bridge will integrate Intel's newest graphics chip technology directly onto the central processing unit. November 15, 2010, Wolfram Research released Mathematica 8 with OpenCL LINK package. March 3, 2011, Khronos Group announces the formation of the WebCL working group to explore defining a JavaScript binding to OpenCL. This creates the potential to harness GPU and multi-core CPU parallel processing from a web browser. March 31, 2011, IBM released a fully conformant version of OpenCL 1.1. April 25, 2011, IBM released OpenCL Common Runtime v0.1 for Linux on x86 architecture. May 4, 2011, Nokia Research releases an open-source WebCL extension for the Firefox web browser, providing a JavaScript binding to OpenCL. July 1, 2011, Samsung Electronics releases an open-source prototype implementation of WebCL for WebKit, providing a JavaScript binding to OpenCL. August 8, 2011, AMD released the OpenCL-driven AMD Accelerated Parallel Processing Software Development Kit v2.5, replacing the ATI Stream SDK as technology and concept. December 12, 2011, AMD released AMD APP SDK v2.6, which contains a preview of OpenCL 1.2. February 27, 2012, the Portland Group released the PGI OpenCL compiler for multi-core ARM CPUs. April 17, 2012, Khronos released a WebCL working draft. May 6, 2013, Altera released the Altera SDK for OpenCL, version 13.0. It is conformant to OpenCL 1.0. November 18, 2013, Khronos announced that the specification for OpenCL 2.0 had been finalized. March 19, 2014, Khronos releases the WebCL 1.0 specification, OpenCL C language. The programming language used to write computation kernels is called OpenCL C and is based on C99, but adapted to fit the device model in OpenCL. The memory region qualifiers global, local, constant, and private on pointers determine where in the memory hierarchy the buffers that they point to reside, and functions can be marked kernel to signal that they are entry points into the program to be called from the host program. OpenCL C emits function pointers, bit fields and variable length arrays, and forbids recursion. The C standard library is replaced by a custom set of standard functions, geared toward math programming. OpenCL C is extended to facilitate use of parallelism with vector types and operations, synchronization, and functions to work with work items and workgroups. In particular, besides scalar types such as float and double, which behave similarly to the corresponding types in C, OpenCL provides fixed-length vector types such as float-4. Such vector types are available in lengths 2, 3, 4, 8 and 16 for various base types. Vectorized operations on these types are intended to map onto SIMD instruction sets, for example SSE or VMX when running OpenCL programs on CPUs. Example, computing the FFT. This example will load a fast Fourier transform implementation and execute it. The implementation is shown below. The actual calculation. A full, open-source implementation of an OpenCL FFT can be found on Apple's website. OpenCL conformant products. The Khronos Group maintains an extended list of OpenCL conformant products. Extensions. Some vendors provide extended functionality over the standard OpenCL specification via the means of extensions. These are still specified by Khronos but provided by vendors within their SDKs. They often contain features that are to be implemented in the future. For example, device fission functionality was originally an extension but is now provided as part of the 1.2 specification. Extensions provided in the 1.2 specification include writing to 3D image memory objects, half-precision floating point format, sharing memory objects with OpenGL, creating event objects from GL sync objects, sharing memory objects with Direct3D 10, DX9 media surface sharing, sharing memory objects with Direct3D 11, device fission, introduced fully into the OpenCL standard with version 1.2, allows individual command queues to be used for specific areas of a device. For example, within the Intel SDK, a command queue can be created that maps directly to an individual core. AMD also provides functionality for device fission, also originally as an extension. Device fission can be used where the availability of compute is required reliably, such as in a latency-sensitive environment. Fission effectively reserves areas of the device for computation. Portability, performance and alternatives. A key feature of OpenCL is portability, via its abstracted memory and execution model, and the programmer is not able to directly use hardware-specific technologies such as inline parallel thread execution for NVIDIA GPUs unless they are willing to give up direct portability on other platforms. It is possible to run any OpenCL kernel on any conformant implementation. However, performance of the kernel is not necessarily portable across platforms. Existing implementations have been shown to be competitive when kernel code is properly tuned, though, and auto-tuning has been suggested as a solution to the performance portability problem, yielding acceptable levels of performance in experimental linear algebra kernels. Portability of an entire application containing multiple kernels with differing behaviors was also studied, and shows that portability only required limited trade-offs. Furthermore, in studies of straightforward translation of CUDA programs to OpenCL C programs, CUDA has been found to outperform OpenCL. But the performance differences can mostly be attributed to differences in the programming model and in the optimizations that OpenCL C compilers performed as compared to those in the CUDA compiler. See also. References. External links, official website for OpenCL. Official website for WebCL.